sometimes you'll see it spelt like a hospital, but it is a silent S. And so this is a little bit of history just for you, because I kind of thought I'd put that in there. So he figured out that if you use derivatives to help evaluate limits involving indeterminate forms. Does anybody remember what an indeterminate form was? We learned it in grade 12 pre-cal.
0 over 0.
0 over 0. Does anybody know another one? Oh, is it like all there? Oh, shit. Okay, how about name one that's not there then?
Some number?
Huh?
1 over what?
No, 1 over 1 is...
Some number?
1 over 0 would not be an indeterminate form, because that would be undefined.
Infinity over 0.
Infinity over 0. No. Think about a power.
0 to the power 0.
0 to the power 0. Very good.
Infinity to the power 0.
And infinity to the power infinity. Very good. Yeah. Yeah. Okay. So, application or repeated application of the rule converts an indeterminate form to a determinate form, and we can actually evaluate the limit really easily. And the nice thing about this is if you have an indeterminate form, what you do you remember thinking back to the limits? You got 0 over 0, and that was the red flag. You had to do something else like factor or the conjugate and stuff like that. Technically, you could use L'Hopital's rule for it. Now, just so you know, L'Hopital's rule, if it is in a free response, you have to prove that you can actually apply L'Hopital's rule to use it. Meaning, you have to actually have it evaluate the limit and get 0 over 0 or infinity or over infinity. And then you have to write it as two separate limits on top of each other. So again, the rule is named after 17th century French mathematician Guillaume de L'Hopital. However, it's believed that the rule actually was discovered by Johann Bernoulli. So, I don't know. Sometimes people are named after things and then they find out later it wasn't even that person. So, in this lesson, we're going to use L'Hopital's rule for calculating limits. So, L'Hopital's rule only applies for these indeterminate forms. 0 over 0, infinity over infinity, or negative infinity over positive, like any form of infinity over infinity, okay? So, if we're finding the limit and we get 0 over 0 or plus or minus infinity over infinity, we can apply it. We denote it by using this h with square brackets above the equal sign, and then we write the limit again. Okay, so, and the rule, I've looked this up for the AP exam. In order to use it, you have to actually show the first step is 0 over 0, say indeterminate form, apply L'Hopital's rule. Okay, so does everybody see if I put 0 in, I get cos of 0, which is 1 minus 1 over, I put 0 in here, I get 0, so I get 0 over 0, which is indeterminate form. Now, normally we would say, oh, we need to factor or do the conjugate or whatever. That was the rule when we did limits a long time ago, right? But you can see right here, maybe you could do a conjugate and you went somewhere with it, right? You could multiply by cos x plus 1 over cos x plus 1, right? But I'm going to show you kind of a cool thing is that we can do what's called L'Hopital's rule, which means we split the limit up and we find the derivative of the top and the derivative of the bottom. So apply L'Hopital's rule. No. Because remember, the rule of limits is you can actually apply the limits separately. It's not an actual quotient rule. So that means the limit as x goes to 0 of cos x minus 1 over sine x equals, now we're going to put this h on there as the limit as x goes to 0. Now what we're going to do when we apply L'Hopital's rule is we're actually finding the derivative of cos x minus 1. So what's the derivative of cos x minus 1? Negative sine x? Okay, and then what's the derivative of sine x? Cos x, yeah. So now we're going to actually, and actually the way they want it is we're actually going to apply the limit separately. So technically I should be writing the limit twice. I'll do that in the next one. It's not a big deal. Okay, so 0, what's sine of 0? What's cos of 0? 1. So we actually get negative 0 over 1, which is a legitimate answer of 0. I'm sorry? Just for fun, like back, I know you like doing lots of math fun stuff, and I know this lesson isn't too long. Remember back in the day when we did these limits, and we got cos x minus 1 over sine x, and we got 0 over 0, we were supposed to do something more, right? So then we would say maybe try this, cos x plus 1 over cos x plus 1. Something like that.
That would evaluate.
So then we get limit as x goes to 0. We get what? Cos squared x minus 1 over sine x times cos x. Remember we didn't multiply that through. And then what do we try to do after that? Yeah, it's turn that into sine squared. So remember that this is what we used to do. So remember sine squared plus cos squared x equals 1. So if I wanted cos squared x minus 1, that would be, does everybody see? This would be minus sine squared x, yes? So I'm going to rewrite this as, I'm just kind of trying to show you guys that you get the same answer, but this is way simpler now, right? So you get minus sine squared x over sine x times cos x plus 1. That would cancel that, right? And we get the limit as x goes to 0 of minus sine x over cos x plus 1. Now if I sub this in, what do I get? 0 on top, or minus 0 if you want, but and then if I put 0 in here, I get 2, which gives me 0. Do you see? I get the same answer, but this was way easier now. Yes? Okay, but I couldn't have shown you L'Hopital's rule when we did limits because we didn't know what derivatives were yet, right? So next one, if I substitute 0 in, I get 0 minus 0 over 0, which is 0 over 0. Indeterminate form. We're going to use L'Hopital's rule. Well, if this is a free response, yes. It's a name, so you would capitalize it, right? So the limit, so therefore the limit as x goes to 0 of sine x minus x over x cubed, I'm going to apply L'Hopital's rule by putting the h. And then this time I'm actually going to do it as the limit on top and the bottom, just so you know, because that's what you're supposed to be doing, even though it seems like it's supposed to be written as a quotient of limits once you do this, right? Okay, so what is the derivative of sine x? Cos x. And what's the derivative of minus x? Minus 1. And what's the derivative of x cubed? 3x squared. So what do we get now?
Still 0 over 0.
0 over 0. So that is apply again. You can do this as many times as you want until it works. Well, hopefully you don't do the wrong answer. So this is the limit as x goes to 0. Well, if you keep on going forever,
you'll eventually reach a point where nothing changes.
Actually, the only when I taught the U of W calculus, we get into more in-depth L'Hopital's rule, where you actually do the L'Hopital's rule so many times that you actually go back to the beginning of what you started, and then there's an actual application that you do after that. Yeah. Okay, what's the derivative of cos x? negative sine x. And what's the derivative of 3x squared? 6x. Okay, so now if I apply that, what do we get? I get 0 over 0 again. So I'll apply again. So this time it actually works. Can you tell because the 0 is going away at the bottom, right? So the limit as x goes to 0, limit as x goes to 0. And so derivative of sine x is, yeah, so it still have a negative, so negative cos x, and this would be over 6. So I apply the 0, I get negative 1 over 6. It's kind of cool, hey? The derivative of the inverse of sine. Well, first off, we have to, of course, if I put 0, I get 0 over, what's the inverse sine of 0? No, that's not 1 over. The inverse sine means what angle gives me a ratio of that. So that's when, no, it's 0. It's 0, right? It's right at the start that the height is 0, right? Okay, so then indeterminate, apply. No, there's a we already learned what the derivative of inverse sine is, right? What is that?
No, I'm talking about how you get to 0.
How did I get this 0? Inverse of sine. 0.
How did you?
Okay, so what's the, so limit as x goes to 0.
1 over the square root of 1 minus x squared.
Okay, well first off, this is 2x, right? And so the derivative inverse sine is 1 over the square root of,
1 minus.
yes, you should know this. Yeah, it's 1 minus. 1 minus x squared. Tan is the plus. And I know when we get into integrals, I kind of go over, tan doesn't have the square root either, right? And I remember the tan, the t looks like a plus sign, right? So that's how I always remember, what's the tan at the plus? Because it actually makes more sense when we're integrating versus finding the derivative. But anyways, so if I put 0 in there and 0 in there, I get 0 divided by 1, which is a legit answer, 0, right? No, we didn't have to do it again. Okay, so, okay, so secant of pi over 2, so secant of pi over 2 is
Give me a 0 for 0.
there should be probably a plus sign there, but it's missing. But anyways, is it what?
Well, no, see this.
Okay, so hold on.
But they said when you count,
I was thinking tan of 0, not tan of
I took tan of.
Okay, so secant of pi over 2 is what, first off?
Undefined.
Cos is 0. It would be 1 over 0, right? Okay, so this is 1 over 0, and then this is,
Yeah, we're actually going with it.
so what's tan of pi over 2?
So that's 1 over 1 plus.
No.
That's what?
Because it's sine x over cos x times the 1 and cos would be 0, so it'd be 1 over 0 plus 1. So
Okay, so this is 1 plus, this would be 1 over 0, right? Okay, so this is not in L'Hopital's form to be able to do this, right? Like you can't just arbitrarily apply L'Hopital's rule and hope for the best. So sometimes we have to manipulate it so that it actually works out. So now let's think about this graph here, and I'm pretty sure it should have a plus there. 1 divided by 0, if you think about the graph, I know it's undefined, but think about the graph. That's why I'm saying I think it has to be a plus there for this actually to work. Meaning we're not finding the limits on both sides because they're actually going like this, right? So I think there's a typo there. It should have a plus. So what is that actually, like if you think about the graph? So, so just so remember, cos graph is going like this, right? And so this is where the pi over 2 is, right? And so that's where we get the asymptotes. Maybe I should put it on the minus, but it doesn't really matter. Anyways, so if I do a secant graph, what happens? The ones stay as ones, smaller becomes bigger, and it looks like this, right? Do you remember that? So if I'm coming from the right hand of pi over 2, I get negative infinity, right? And then if I have tan x, so let's remember what a tan graph looks like. Tan of 0 is 0, and at pi over 2 we have the asymptote, and it looks like this, right? So then that is over positive infinity. Yes?
Isn't it coming from the other side?
Oh, yeah. Sorry, it is. So this is negative infinity. Yeah. In a way, you'll get the indeterminate form. So this is indeterminate form. Determinate form. Because you can't add 1 to negative infinity, right? For me, it'll be okay, but for like if it's on the free response, but for the exam, I just write it out because they're so picky or whatever. So apply L'Hopital's rule. Somehow you have to show it's an indeterminate form. Somehow. Okay, so what is the derivative of secant? What's the derivative of secant? Not negative. That's the CCC is the minus, is positive. Okay, so what's the derivative of 1? 0. What's the derivative of tan? Huh? Secant squared, yep. Secant squared x. So this will cancel with that. Yes?
Yeah.
And so, what do we get then? We're going to get another indeterminate form, aren't we? We're going to get infinity over infinity again, negative infinity over negative infinity. So, apply again. Indeterminate form, apply. Huh?
at the end, like at the end, you go over how you got the negative form.
You just write negative.
Sorry, I'm not recording. Just because we did a L'Hopital's rule doesn't mean we need to do L'Hopital's rule, because I'm thinking this is just going to get us more in deeper and deeper, right? Like, think about this. Even though this cancels, it's like Josh is saying, it's kind of flipping back and forth. Tan, though, is sine x over cos x, and secant x is, so if we're, is 1 over cos x, which means these will cancel, right?
Yeah. Just
So it's just sine x. So then this is just simplified to be the limit as x goes to pi over 2, we'll say from the right, of sine x. And that, of course, is 1. Yay! Okay. Oh, now we need to know what... remember what the logarithm graph looks like?
Yeah.
That's a logarithm graph, right? So it says when x goes to infinity, that would be the far right. What would ln of that be? Huh? What? It would be infinity. And then what if I put infinity in there? Like I normally, if we have x goes to infinity, we have that technique for limits that we pull out the highest degree and all this stuff. But in this case, it's not going to get us anywhere. Do you see 2 times infinity is still just infinity? So we have the indeterminate form. Okay, so that means we're going to apply lHopital's rule. The hardest thing about lHopital's rule is it'll be mixed somewhere in the exam and you won't know where it's going to show up, right? So...
Someone in the exam is going to figure out where it is.
Okay.
And so you're saying if we don't use it, then they're gonna.
It's just going to be hard.
I guess what I'm saying is I'm making sure it's on the test, of course, because this is one of the outcomes we're doing. But on the exam, because it's so like intense of what they test, there might be one question on there. Will you find it? I don't know. Like you only have 2 minutes of multiple choice question, right? So anyways, who remembers what the derivative of ln x is? Very good, Rachel. 1 over x. Okay, so what would the derivative of 2? I want to write 2. The square root of x is the same thing as 2x to the power of half, right? So what would the derivative of that be? Yeah, 1x to the power negative a half. We need to simplify that, right? So what do we get when we simplify that? Well, this is a negative. So this negative as positive will go to the top, right? And so then we would have, maybe we should just rewrite it at this point just to show you. So this would be x to the power a half over, and then this would go on the bottom as x to the power 1. Yes? And you could say, well, I could simplify it, and then I could get, with the x's, what would I get? Well, or you could have 1 over x to the power half, right? Is everybody good with that? So I'm going to... If you do it right now, does everybody see? You could leave it as indeterminate form, right? And then apply again. So you have an option, because you get infinity over infinity right now. And so that would be indeterminate form. Then when you found the derivative separately, this would go to 1. And then you wouldn't have an indeterminate form anymore. And then this would go to 1/2 x to the power negative a half, which puts it at the bottom, which is exactly what's happening right now. Do you see? This would be 1 over x to the power a half. If I put infinity in, what do I get?
0.
Yeah, 1 over infinity, which is 0. A lot of these answers end up being 0, it seems, hey?
Yeah.
So if you have no clue, don't pick infinity, pick 0. You'd be better off, right?